In this example, we are given the two masses M1 and M2 are suspended from a spring of force constant K as shown in equilibrium. Here, if mass M1 is removed from the system and M2 is released, we are required to find the angular frequency and amplitude of SHM of M2. Here you can see if the two masses are hanging in equilibrium, the spring must be extended from its natural length, say by a distance h1. So we can state at equilibrium m1 plus m2g, the total weight is being balanced by the force of a spring kh1. h1 is the extension from its natural length due to the weight of the two blocks. Now if m1 is removed, the new equilibrium position will no longer be the same because the overall weight is reduced. So we can simply state the equilibrium position for M2 would be somewhere at a higher position where the extension of a spring would be H2. So we can state after removal of M1, new equilibrium position changes such that now we can write M2g is equals to KH2, where H2 is the distance of new equilibrium position from the natural length of a spring. So we can state when M1 is removed and M2 is released, so M2 is released from a distance H1 and its equilibrium position is H2. So this will be the amplitude of oscillation for M2, or we can say M2 is released from its lower extreme position. So we can directly write new oscillation amplitude for M2 is this amplitude of oscillation can be written as H1 minus H2. So when we substitute the values of H1 and H2 here, we can see H1 is M1 plus M2 into G by K minus H2 is M2 G by K. So this will give us M1 G by K. That will be the answer of this problem, as M2 will oscillate with this amplitude and only M2 is oscillating under the influence of the spring having a force constant K. So we can write angular frequency for SHM of M2 is this omega, as we already studied, can be given as root of K by M2, because under the influence of a spring of force constant K, M2 is oscillating. This will be another answer of this problem.